In this, we're going to talk about a very special case. So there are certain matrices for which it is impossible to find n linearly independent eigenvectors. So in that case, what's going to happen? We're going to find what we call generalized eigenvectors or generalized vectors. So let's discuss the idea. So let's say for some n by n matrices, it is impossible. It is impossible to find. It is impossible to find n linearly independent eigenvectors. Eigenvectors. So it's impossible to find linearly independent eigenvectors. In these cases, we can find what we call generalized eigenvectors. For such matrices, we find generalized vectors. Generalized vectors. So let's see how we can do it in a problem, and also we can use a shortcut here. Uh, so use a shortcut method. So what's a shortcut method? So let's talk about shortcut method for a 3 by 3. For a 3 by 3 matrix A, for a 3 by 3 matrix, if the eigenvalues are lambda 1, lambda 2 and lambda 3, not necessarily distinct, they may be the same, equal. We know that if the eigenvalues are lambda 1 and 2, we know that a minus lambda 1 I times a minus lambda 2 I times a minus lambda 3 I equal to 0. So this is by the Cayley-Hamilton theorem, by Cayley-Hamilton theorem. Because Cayley-Hamilton theorem says that A is a solution of the current characteristic equation, and the characteristic equation can be factored, and these are 3 factors. So that's what it says. So but now we can have a second look at this one. For example, what this says, if you isolate 2 products, these matrices we call the eigenmatrices. So if you look at the product of 2 eigenmatrices, the non-zero columns of those 2 are the eigenvectors of the other one. So that means so non-zero columns of the product is a product. If you multiply these two, you again get a 3 by 3 matrix. Okay, so non-zero columns of the product eigenvectors of lambda 1. So we can do the same thing because this product is commutative. That means you can rearrange them. So you can come. It doesn't work with regular matrices, but for eigenmatrices, this product is commutative. So you can rearrange. So that means if you need the eigenvector of lambda 2, what you're gonna do? You're gonna multiply the first one and the third one, and then look at the non-zero columns. Those are the eigenvectors of lambda 2. If you need eigenvectors of lambda 3, you're going to multiply the first one and the second one, and then if there are non-zero columns, those non-zero columns are the eigenvectors of lambda 3. So that's the argument. So let's see this in a problem. So let's look at this one. So let's find so if a matrix doesn't have enough eigenvectors, like for example, if we have n by matrix, if it doesn't have n linearly independent eigenvectors, we call such a matrix is a defective matrix. So let's write that. Yeah. So there are no if there are no n linearly independent linearly independent linearly independent eigenvectors, uh, linearly independent eigenvectors, if there are no n linearly independent eigenvectors of a matrix A, n by n matrix A, uh, the matrix is called defective. Okay. So let's try to look at let's see how to find the eigenvectors and the generalized vectors for such a defective matrix. So let's look at this one. So the example, find eigenvectors and generalized vectors of the matrix A, which is 5 4 0 1 0 2 0 2 5. The first thing is always find eigenvalues. So the first step, find eigenvalues. For that, what we normally do is we can look at the characteristic equation. So that's the determinant of A minus lambda I. So that means you subtract lambda from the diagonal entries and they take the determinant. So it's a determinant of 5 minus lambda and then negative for 0 and then 1. You subtract lambda from the diagonal entries is negative lambda 2 and then 0 to 5 minus lambda. Now what we can do, we can look at the expansion of this one. We can use the cofactor expansion of this one. So I'm going to use the first row. So if I use the first row, what's going to happen? So we're going to go with plus, minus, plus. Those are the sign convention. So you're going to get 5 minus lambda times the minor, which is negative lambda. So we're going to delete the first row and the first column. So you end up with this. And then we have minus, and then we again have so we have minus 4. So that means going to be yeah, let's write it minus 4. We can read the first row and the second column. So you're going to get 1 0 2 5 minus lambda, and then we can simplify this one. So once you simplify, what you're going to get is 5 minus lambda times, here you're going to get so when you expand, when you multiply these two, you're going to get lambda squared minus 5 lambda minus 4, and then here you're going to get plus 4 times, you're going to multiply that, so you're going to get plus 4 times 5 minus lambda. Now what you can do, you can simplify this. So you can see lambda minus 5 is a factor. So let's take it out. That's always a good idea to take the factors out rather than simplifying, because you are looking for the factors. So we are not going to distribute, we can take the factors out. So once you take the factors out, you're going to get the determinant of A minus lambda I. So you can take the factor out. So you can take 5 minus lambda as a factor. What you end up getting is lambda squared minus 5 lambda because 4 get cancelled. And you can see this is very easy to find factors. So we're going to find the factors. So lambda is a factor, and then we have uh, 5 minus lambda and lambda minus 5. So we can take the minus sign out. So it is lambda minus 5 squared. Now you see this equal to 0. So the zeros of these are the eigenvalues. So the eigenvalues are lambda equal 0, 5 and 5. So we write it like that just to exaggerate that 5 repeats. So we do that. Okay, now what we can do, we can shortcut method. That means we can look at the eigenmatrices. Uh, so write eigenmatrix product. So what's eigenmatrices for these? So lambda is 0, so we can write kappa 0 a times kappa 5 0. We only like the product for different eigenvalues. So by the definition, what it did, this means a minus 0 times I. That means simply a times a minus 5 times I. Those are the kappa matrices. So let's do that. So that means a. So that is 5, negative 4, 0, 1, 0, 2, and then 0, 2, 5. That's the first one. And then multiply with the next one, a minus 5. What is a minus 5? You subtract 5 from the diagonal entry. That means 0, negative 4, 0, and then 1, negative 5, 2, and then 0, 2, 0. That's what you get. Now what we can do, we can multiply them. So let's multiply. If you multiply with the first column of the second matrix, you can see you only get the second term in each row. So that means you get negative 4, 0, and 2. And now you go to the second row. In the second row, you get 5 minus negative 4, negative 4 times 5. So it is negative 20 positive 20, that means 0. And then if you go to the second column, you're going to get negative 4, and the positive 4 is 0. And if you go to the last row of the first matrix, you're going to get 0, and then negative 10, positive 10, 0. It's a 0. It means something. And then go to the last column. So if you go to the last column, so what you get is so 0 times 5 is 0, negative 4 times 2 is negative 8. So you're gonna get negative 8, and then you get 0 here, and then in the bottom last one, 0 times 0, and then 2 times 2 is 4, and then so you get 4. So that's what you get, and you can see that this is not equal to 0. So not equal to 0 means you cannot just get the eigenvectors, but you can get some. So let's look at few things. For example, this is a 0. This is a 0 means how to get that column. To get that column, you multiply this column with the first matrix. So that means this is a eigenvector of lambda equals 0. So this eigenvector of lambda equals 0. Why? When you multiply that column with the first eigenmatrix, that eigenmatrix is corresponds to lambda equals 0. So you get a 0. That means this is an eigenvector of lambda equals 0. And then what else we can see? And then we can also see that this product has some non-zero columns. Those non-zero columns are the eigenvector of the one that we missed. You know that if you look at the whole product has what we have in the complete product. You have kappa 0 a, and then kappa 5a, and then the kappa 5a. We know that by the Cayley-Hamilton this is 0. That means if you look at just two of them, the non-zero columns are eigenvectors of the one we miss. So that means if you look at non-zero vector, any non-zero vector, or even like a scaling one, so you can pick any of them. You can see they are multiple of each other. So that is an eigenvector of the missing one. That means eigenvector of lambda equals 5. So we just get that. Also, you can even scale this one. So for example, you can say you can divide this one by -2, so you can simply write as 2 0 -1. Okay, that's much easier to simplify. So that's the eigenvector of lambda equal 5. So the question is, there are no more. Because that's just the multiplication of the other one. They are multiple of each other. That means there are no more eigenvectors. So that's the problem. So you can see you're gonna stuck with only 2 eigenvectors. So the question is how to find the other eigenvector. So there are no more eigenvectors. So we need to find a generalized vector. To do that, we're gonna use a new technique. We can use the standard argument for generalized vectors. So let's talk about that to find another vector, because we need one more vector for 5, because 5 has multiplicity 2. 5 has multiplicity 2, so that means we need one more vector for 5. To do that, we're going to calculate what we call a generalized vector. So let's talk about that part. So let's say to find a generalized vector, to find a generalized vector. So what we can do, let's use the standard argument. So let V be an eigenvector. Let's be an eigenvector of lambda equal 5. Okay, let lambda, and then another linearly independent, it's very important, another linearly independent vector can be found by this equation. What we're going to do, we're going to solve this equation by solving a minus 5i times u equal v. So we're going to solve this equation. There's another vector, we call this the generalized vector of lambda equal 5. Okay, by solving for u. So let's do that. We're going to solve. So we're going to use a simple linear algebra arguments. What we're going to do, we're going to look at a minus 5i augmented with v and do the row reduction. So we can do the row reduction. So that's going to give you the u vector. So let's do that. So we can start with 0, -4, 0, 1, -5, 2, and 0 to 0 augmented with v. We're going to assume v equal 0, 2, 0, -1. That's what we picked as v. So that's the eigenvector of lambda equal 5. So now we can do the row reduction. So any order you like. So what we can do, we can interchange. First we can add. We can interchange the first row with the second row, and also at the same time you can add the multiple of the third row to the first row. So you can do that. So if you add multiple of the second row to the first row, so I'm going to do a few steps at the same time. Okay, let's first switch. Let's put interchange the first two rows. So then you're going to have 1, -5, 2, 0. So that you did, you interchange row 1 with row 2 as the first step. And then what I do, I'm going to add 2 times row 1 to row 2. So add 2 times row 3, actually 2 times row 3 to row 2, the new row 2. If you do that, what's going to happen is you can see you get a 0. Yeah, so you get a 0, 0, 0, 0, and then you have 0, 2, 0, -1. Now what we can do is we can switch the two rows, and also we can divide by 1/2. Okay, so you can do two things. So now the next thing what we're gonna do is we're gonna have 1, -5, 2, 0. We're gonna switch the two rows and also divide by half. So I'm gonna do two things. I'm gonna switch R2 with R3, and then I'm going to take half of the new R2. So if you do that, you simply get 0, 1, 0. Actually, we miss few things here. So let's write the rest of the terms before forget. So we have 0 here, and we take the half. This is going to be a -1/2, and it becomes 0, 0, 0. That's what we have. So how we get that? We first switch R2 with R3, and then take half of and then take the half of row 2. After we do that, then take the half of row 2. So I just write it to avoid unnecessary writing. Okay, then this is what you get after we do that. Now what we're gonna do, we're gonna add 5 times of the row 2 to row 1. So if you do that, then you simply end up getting 1. Okay, so what we do, you'd add 5 times row 2 to row 1. So if you do that, you get 0, 1, 0, 2, and then you're gonna get -5/2. This is 0, 1, 0, -1/2, 0, 0, 0, 0. That's what we get. Okay, now we get the echelon form. Now what we're gonna do is we're gonna write the corresponding system. So write the system. So the next step is write the system. So if you write the system, you're gonna get x1 plus 2x3 equal -5/2, and then you also get x2 equal -1/2, and x3 is free. So what we can do is, for the free variable we can pick 0. So let x3 equals 0. So if you pick x3 equals 0, then x1 becomes -5/2, and x2 becomes -1/2. So that means we have all the numbers. So the vector, so we can write the vector is we can say v equal, which has 3 components, x1, x2, x3, which is x1 equal -5/2, and then x2 is -1/2, and then this is 0. So that's the vector, and we cannot scale this because this is not a eigenvector, so we are not going to scale this one. We leave it like that with all the negatives and fractions. So that is the third vector, and then this gonna create, I'm gonna call this 3. This gonna create a 3 linearly independent vectors for the matrix. So the 3 linearly independent vectors for A is, we have v1, which is an eigenvector for lambda equals 0. So that was 4, 5, -2, and then the eigenvector for lambda equal 5, which was 2, 0, 1, the scale version, and then after that the corresponding vector for this, which is v3, we can call it's not eigenvector, so we don't call it. That's just a generalized vector. It is 5/2, -1/2, 0. So this is a generalized vector, but those 3 are linearly independent. And you can see that where the 0 is in the second and third, you can see that it's clearly linearly independent. Okay, so this is how we find the three vectors.